Hello everyone, I'm Yihao from Peking University. Today, I'm glad to share our work Klotski, efficient and safe network migration of large production data centers. This is joint work with my co-authors from Meta, Johns Hopkins University, and Peking University. Large web service providers heavily depend on data center networks to deliver reliable and smooth experience to users. Data center networks are constantly scaling and evolving because of at least three reasons. First, the data center traffic is increasing at a fast pace under new technology trends, like large language models. Second, switch failures are the norm rather than the exception in large-scale multi-layer data center networks. Third, there are routine procedures to retire old hardware and onboard new hardware. The scaling and evolution of data center networks rely on network migration, which changes the network by draining, undraining, or swapping switches and circuits. Unlike operating on the control plane or data plane, network migration involves physical deployment work, that is, a manual process performed by human operators, making it more time-consuming and complicated. The objective for network operators is to perform network migration efficiently and safely. For efficiency, we need to minimize the time of generating migration plans and performing migration. For safety, we need to satisfy dynamic traffic demand and absorb traffic bursts during the migration. At Meta, there are three large-scale migration types that have happened in the past few years. These migrations replace or add switches in different layers, and we name them H-grade V1 to V2 migration, SSW forklift migration, and DMAG migration. These migration types involve hundreds of switches, tens of thousands of circuits, tens of terabytes, and can take several months. So why is the network migration hard? First is the efficiency requirements. Here, we consider both the time to generate the migration plan and the time to finish the migration plan. Second, the data center network architecture is complex and evolving. At Meta, there are 8 layers and more than 9 types of switches, which is more complicated than conventional glass network topologies. Besides, multiple generations of switches, circuits, and routing protocols may coexist in a single migration task. Third, various operational requirements exacerbate the network migration problem. The demand variance is not negligible considering the long duration of migration. The traffic grows organically over time, and unexpected traffic spikes happen occasionally. Additionally, the total number of ports on the hardware is a hard constraint. A real-world migration task usually involves hundreds of switches per data center. The number of possible migration plans, or the number of permutations of these switches, is more than 157 power of 10. Previous work mainly lies in two categories: greedy-based planner and symmetry-based planner. The greedy-based planner utilizes greedy strategies, but it cannot guarantee the optimality of the migration plans. The symmetry-based planner utilizes the inherent symmetry of data center networks, but it cannot scale to complex migration types and topologies. To solve these challenges, we introduced Klotski, a system for efficient, safe, and optimal data center network migration of large production data centers. Klotski reduces the time to get the optimal migration plan by up to 381 times compared with previous work. It has been deployed at Meta since 2020 and has served 20 regions. Klotski takes constraints, forecasted traffic, original topology, and target topology as input. First, it prunes the large search space by inherent symmetry and locality of data center network architectures, without affecting the optimality. Then, the planner of Klotski computes the optimal migration plan by A-star search algorithm, Specifically, in order to leave room for traffic spikes, the demand constraint requires the utilization rate of each circuit to be lower than a threshold. Besides, the port constraint constrains the number of used ports. The objective of the migration planning is to minimize the operational cost. The operational cost mainly comes from two consecutive actions with different action types. Because in practice, actions with the same time can be operated simultaneously with almost no extra cost. The large number of switches leads to an extremely large search space. Like previous work, we also utilize the symmetry property of switches, which can reduce the number of possible plans. However, there is little symmetry in metadata center networks, making this approach inefficient. We further utilize the locality of switches. One key observation is that operating the switches close to each other simultaneously leads to little extra operational cost and little impact on constraints. Thus, we merge switches with locality into one operation block and operate them together. This greatly prunes the search space. While searching for the optimal plan, the planner needs to check the satisfiability of constraints again and again, even for the same topology, which is time-consuming. We found that the constraint satisfiability is only related to the current topology, no matter what the action sequence is. Thus, we can further reduce the time for checking with a catch table. Searching all states still costs too much time in practice. We leverage the A-star search algorithm with domain-specific priority, which searches states that have smaller estimated operational costs first. Specifically, the estimated operational cost is the existing cost plus the estimated remaining cost. Here, we take the number of remaining action types as the estimated part. This technique further speeds up the search process. Our evaluation is performed with 5 production-level data center network topologies, with up to 10,000 switches and 100,000 circuits. The 3 migration types involve up to 700 actions. We use the historical traffic collected by Meta's data center network. We first evaluate the optimality of the plans. Klotski can always get the optimal migration plan with all topology sizes and migration types evaluated. We also evaluate the efficiency. Klotski reduces the planning time by up to 381 times compared with baselines. Klotski finds the optimal plans for all test cases within 4 minutes, while baselines may not find feasible plans within 24 hours. Next, I'd like to share our operational experience. In some production scenarios, network operators need to create special routing configurations during the migration process to utilize a special intermediate topology. Also, we need to incorporate traffic demand forecasts into the migration process because the migration may take several months and the traffic may increase drastically. Besides the standard demand and port constraints, we also handle with other operational constraints, including the failures during operation duration, simultaneous operations, unspec'd traffic surge, and so on. We also explored various deep learning methods like reinforcement learning and graph neural network. However, we met some practical obstacles, including scalability, efficiency, and reliability issues. To conclude, Klotski is a production system for efficient and safe data center network migration. We formulate the migration planning with domain-specific constraints. We also leverage locality and informed search to improve efficiency. Klotski is actively running at Meta Datacenters. Thank you for listening.